welcome to the last lecture of this week. What we discuss in this week is we try to understand the concept of stress and strain, definition of stress and strain, and then of course, with the assumption that it's a small deformation theory. And then we also studied how to represent stress and strain and different operations on stress and strain. What is the purpose of this week is to just to have a summary of what we have discussed and some important thing that we will be using in the subsequent weeks. We will discuss that today. Okay. So, it is essentially the closure of this week concept of stress and strain. You see, so we define stress and strain as a tensor, stress is a point, strain at a point is a tensor like this. Okay. And then these tensors are a symmetric tensor, second order tensor, symmetric tensor, and similarly for strain as well. Now, then we also discuss, now let us try to understand what is principal stresses. We also discuss that since this tensor can be, this second order tensor, always when we say that it is a stress is represented like this, a strain represented like this, always a coordinate associated with this. Always we represent the stress and strain with respect to some coordinate system, right. For instance, in this case, if it is with respect to x, y, z, a given coordinate system, then the representation is like this. But then if we change the coordinate system, then if we change a coordinate system, say prime coordinate system x dash, y dash, z dash, with respect to that same coordinate system, we can have the representation of the same stress like this, right. Now, you see, now suppose you think of a situation that you have a state of stress at a point which is represented like this, okay, with respect to a given coordinate system, then you are slowly changing the coordinate system, okay. Now, when you slowly change the coordinate system, then what happens is the stresses, the individual components, they also change, right. So, all the normal stresses, all the shear stresses, they also change, either they increase or they decrease, but they change. Now, if you keep on change this coordinate system, then you will come to a point when, or you come across a coordinate system or the rotated coordinate system for which there is no shear strain on this on all these three planes. For instance, if we have any arbitrary coordinate system, we rotate the coordinate system, and then we keep on rotating the coordinate system, and when your coordinate system becomes n1, n2, n3, how to determine n1, n2, n3 and what are these sigma 1, sigma 2, that will come shortly, but let us try to understand what is principal stress through again geometry. So, physically what is happening there. Now, we will come to a point where on these three planes there is no shear stresses. All these shear stresses that we had here, these shear stresses, all these shear stresses, they vanish. Only then we are left with normal stress in three normal direction, and this is sigma 1, sigma 2 and then say sigma 3. These, and then suppose that directions are n1, n2 and n3, all are vector, okay. n1, n2, n3 are the directions. Now, these sigma 1, sigma 2, sigma 3 are called principal stresses, and I believe that you have already learnt it in solid mechanics course. Now, so when we have as I said, this is the representation. If we represent stress like this, for instance, if we represent stress like this, this is with respect to a given coordinate system, right? A given coordinate system. This is x, then y and z. Okay. Now, if we change the coordinate system, if we have a new coordinate system which becomes say it is n1, n2 and n3, something like this, and with respect to this coordinate system there are no shear stresses, only the normal stresses, then what will happen is all these diagonal terms, they become 0, and the stress tensor essentially become only a diagonal matrix where this is sigma 1, sigma 2 and sigma 3. Okay. That is the strain when you have. So, this is the stress tensor with respect to the principal plane n1, n2, n3 with respect to principal plane. Now, you recall the invariant invariant, they do not depend on the coordinate axis you choose, and there are 3 invariants for stress tensor, the second order stress tensor. The first one is the trace of the matrix, since it is invariant. So, whether you calculate the stress with respect to xyz coordinate system or n1 into n3 coordinate system, they remain same. The invariant with respect to principal coordinate system is sigma 1, sigma 2, sigma 3, and similarly the second invariant, which is the sum of cofactors, this is sigma 1, this is this, and the third invariant is sigma 1, sigma 2, sigma 3, the diagonal thumb. Now the question is how to determine this principal stress. If you recall, the principal stress can be obtained by the eigenvalue analysis of this matrix. And what is this eigenvalue analysis? Eigenvalue analysis is that if we have this sigma, any matrix, then eigenvalues can be determined by lambda into I. Lambda I is the identity matrix. The determinant of this will be equal to 0, right? Now, this can be written in initial form as initial form. If I have to write it, then this will be something, this can be written in initial form, that determinant of say sigma I j minus lambda delta I j, that is equal to 0. That is the same thing written in initial form. Now, when you express this, then what happens? Then you get an equation like this, okay, and or before that that equation can be expressed as like this in terms of this invariant, and we solve this equation. You have 3 roots, lambda 1, lambda 2, lambda 3, and these 3 roots are essentially your 3 principal axes, the lambda 1, lambda 2 and lambda 3. Now, the eigenvalues give you the principal stresses. Similarly, you can have the eigenvectors associated with each eigenvalue. Eigenvectors are essentially corresponding n1, n2, n3. Okay. So, this we already know. Now, at this point, so this is called characteristic equation. This equation is called characteristic equation. What is that equation written? Now, just to for the completeness of the discussion, there is a theorem called use different color, Cayley-Hamilton theorem, which says that if this is the characteristic equation, that the sigma itself satisfied, if you substitute sigma in case of lambda, this sigma also satisfies this equation. Okay, we do not need it right now or probably in this course, but just for the completeness you can look into it and then see what this theorem exactly says. Okay. Now, so now let us similar exercise we can do it for strain. So, again we have a principal strain in 3 directions, epsilon 1, epsilon 2, epsilon 3, corresponding invariant. The similar way we can define invariance for strain with respect to any coordinate system. You define the strain, your invariants remain unchanged, and those invariants are same. The first invariance is stress of this and the second invariance is the sum of cofactor, and the third one is the determinant. And similarly, these epsilon 1, epsilon 2, epsilon 3 can be obtained by the eigenvalue analysis, and this is the corresponding characteristic equation. Okay. Now, n1, you please note that in these directions the eigenvalues are epsilon 1, epsilon 2, epsilon 3, and the corresponding eigenvectors gives you n1 tilde, n2 tilde and n3 tilde, where these are the principal direction. Now, you see, now we have stress tensor, we have strain tensor, we know what are the principal stresses, how to determine principal stresses, we know how to determine principal strains, what are the principal directions. Now, the question comes here is, we will not even try to answer this question right now. You have to wait for a couple of weeks to come to that point. The question is, suppose I know the state of stress at a point, and at a given point I know the state of stress and also the state of strain, right. Now, I determine the principal stresses with this eigenvalue analysis with these eigenvalues, and then I determine the principal strain, and then I also determine the direction of principal stresses and the direction of principal strain. Now, the question is whether these 2 directions, the direction of principal stress and the direction of principal strain, are the same or different. You can write this question and put a star mark. We will not answer this question right now. Let us spend a couple of weeks, try to understand what are the different kinds of material, what is and what are the stress strain relation, and then we will try to understand whether under what circumstances, first of all whether they are same or not, and if they are same, then if they are not same, then under what circumstances they can be made same. We will discuss that in subsequent weeks. Okay. Now, this is another important thing. Suppose this is a stress tensor. This stress tensor can be divided into divided into two parts. You see, one is this and another one is this. If you add them, you get this. This part is called hydrostatic part. Hydrostatic part or spherical part sometime also, and this is called deviatoric part. Hydrostatic part, why it is hydrostatic part? You see that all the components, all the normal stresses are same, which is very similar to if you an object in under water, and then if we see the pressure in all the directions are same, right? Pressure does not have any specific directions. Pressure is same in all direction. So, all direction this is same. The sigma is essentially the pressure, sometimes called mean stress. So, this is, that is why it is called hydrostatic part, and this is called deviatoric part. Okay. Now, sigma m is can be written as, is generally written as this, sigma x plus sigma y plus sigma z z3. You look at one thing is very interesting here. What is sigma x plus sigma y plus sigma z z? This is the trace of this matrix, means this is I1. So, I1 by 3, sigma n is equal to I1 by 3. You see, we just now we discussed what is the physical interpretation of I1. I1 is essentially give you the pressure, but you see always I1 may not be, always sigma m may not be sigma xs plus sigma yy plus sigma zz. But yes, for this course, yes, it is fine, but you will see there are probably not in the elasticity, but elasticity within the scope of this course, but there are many materials where the pressure, in order to calculate pressure, you need a different set of equations. Those equations are called equation of state, where the pressure depends on the energy, it may depend on temperature, it may depend on other, it may depend on density. So, that is a different thing. Equation of state we will not going to discuss, that is not within the scope of this course. Okay. So, similar exercise we can do it for strain. Strain also can be divided into two parts. One is again hydrostatic part, one is again deviatoric part, and then hydrostatic part is epsilon m is written as is. Again you see this is essentially the first invariant of strain tensor, which is the trace of this. Okay. And then okay. So, you see we are almost at the end of this lecture. So, where do we stand now? Just if a material is subjected to some kind of threat, then as a response to that threat, the stress and strain are essentially two responses. The difference between is the, unlike stress, strain can be perceived, it can be visualized through the senses that we have, but the two are the responses of material to a threat. Okay. Now, the next question is how to find out the relation between these two responses, that how to find out the relation between this stress sigma and then this stress sigma and then corresponding strain. Okay. Suppose, okay, before that you recall, take a problem of a spring. If you recall a spring which is fixed here, and if we apply a force P, okay, or say yes, force F, say F. Okay. Now, suppose the spring constant is this is F. Suppose spring constant is K. Okay. And then with the deformed shape of the spring become, after the spring undergoes deformation, and this deformation is this. Okay. So, suppose if it is x0, and if it is x, then delta x is equal to x minus x0. Okay. Now, you recall we or x minus x 0. So, recall that in mechanics you studied the relation between k, f are essentially f is equal to k into delta x in this case, okay, or sometime f is equal to k x also we say. Okay. Now, if we plot it, that force and displacement, if we plot in displacement here and then force here, then this relation is linear, and this slope gives you k. Okay. Now, and similarly, I mean, if you recall in your plus 2 level when you studied probably the first time stress and strain, if stress is equal to, if you define stress is equal to force by area, if you take a rod which is subjected to some force F and then cross section is A, then sigma is force by area and epsilon is strain was delta L by L, right, change in length by L. And then there you define that sigma is related to epsilon as sigma into E into epsilon or sometimes Y into epsilon, where Y is the Young's, E is the Young's modulus or elastic modulus, and if you plot it here it is epsilon and sigma, this is this, okay, this is E here which is elastic modulus. Okay. Now, so this is the relation between sigma and epsilon. Okay. Now, but now in this case we just do not have one component of strain and one component of stress. We have the 6 stress components and 6 strain components, right. So, we have to find out relation between 6 thus. So, we have to find out relation between this tensor and this tensor. Okay. Now, if this tensor is sigma ij and then epsilon ij is the strain tensor. Okay. Then we can define a now sigma ij, what is the order of this tensor? The sigma ij tensor order is 2 here, it is a 2 order 2, it is also order 2, that is why we have two indices. Okay. Now, we can define a 4th order tensor C I j, or let us write it instead of I j, let us write it K L, okay, C I j K L. Okay. Now, it is a 4th order tensor. So, what happens your so how many components you have? We have 3 to the power 4 means 81 components. Okay. Now, you see where k and l they are repeated index, therefore, essentially they will vanish, they are essentially dummy index. So, essentially you are left with only ij. So, this is a relation, a very general relation between stress and strain, where C is a 4th order, the order is 4th order tensor. Now, this is in a vector in a tensor form. Even if you write in a matrix form, in a very general case, how many stress component we have? We have 9 stress components. Why I am saying 9? Because I do not want to put that symmetry right now, because I want to start with a very general configuration, very general material. Okay. So, we have 9 strain components. Then we have 9 stress component, 9 strain component. So, we have 9 strain component and then 9 stress component, this is sigma, this is epsilon, and this is also related with something C, very similar to C. So, here it is 9, here it is 9. If you write in a matrix form, if you write sigma and epsilon in a vector form, then how many, what is the size of this matrix? 9 cross 9, which is 81 components. Okay. So, whether you do it in a tensorial notation or this form, essentially you are doing the same exercise, but this is more general, and we will try to stick to this representation. So, now here starts the motivation for the next 2 weeks. We have to find out what is the relation between stress and strain, and we have seen that if stress is this and strain is this, these can be related through some through another tensor, fourth order tensor. See, we don't know what is that fourth order tensor. We even don't know whether such tensor exists or not. But suppose if they exist, and we also don't know what are the properties of those tensor. We don't know actually anything. Let us, if we can represent the stress and strain in this form, if we can, then what is this? What is this? How to find out this? See, next 2 weeks we will spend to understand different kinds of material, or rather different idealization of material, and then see what forms did C take for different idealization. Okay. So, I stop here today. So, next class is next class we will discuss is constitutive relation. This relation is essentially called the relation just now we wrote here. This relation is called constitutive relation. So, next class probably will start with this expression sigma ij is equal to C ij KL epsilon KL, and then see how to find out this C and what are the properties that C may have. We will stop here today. See you in the next week. Thank you.